July 1st, 2025, astronomers working at the Atlas telescope in Chile made an incredible discovery. They spotted something racing through our solar system that would challenge everything scientists thought they knew about visitors from space. The scientists named this object 3I Atlas, and from the very first observations, they could tell it was special. 3I Atlas travels through space at an incredible speed of 58 kilometers per second. To help you understand how fast that is, imagine something moving so quickly it could cross the entire United States from coast to coast in just 2 minutes. Nothing humans have ever built moves anywhere near this fast. This visitor from beyond our solar system makes our fastest rockets look like snails. The object follows what scientists call a hyperbolic trajectory. This fancy term means something very important. Unlike planets, moons, and regular comets that orbit around the sun in circles or ovals, 3I Atlas is following an open path. It came from somewhere else in the galaxy, and after swinging past our sun once, it will leave our solar system forever. The sun's gravity isn't strong enough to capture it and make it orbit. 3I Atlas came from the void between stars, and that's where it's going back. Scientists call objects like this interstellar visitors because they travel between the stars. Finding one is incredibly rare. Throughout all of human history, we've only discovered 3 confirmed interstellar objects. Each one teaches us something new about the universe beyond our solar neighborhood. But 3I Atlas is proving to be the most mysterious and puzzling of them all. When astronomers first started studying 3I Atlas closely, they noticed it wasn't behaving like any comet they had ever seen before. Most comets are basically dirty snowballs floating through space. When they get close to the sun, the ice starts melting and creates those beautiful, glowing tails that people love to photograph. The tails always point away from the sun because solar wind and light pressure push the gas and dust away. This behavior follows basic physics that works the same way for every comet ever studied. Scientists can predict exactly what a normal comet will do based on how far it is from the sun. But 3I Atlas breaks all the rules. The James Webb Space Telescope, the most powerful space telescope ever built, studied the light coming from the comet. What it found shocked the scientific community. 3I Atlas releases way more carbon dioxide than water vapor. Most comets do exactly the opposite. They're mostly water ice with some other materials mixed in. This backward ratio tells scientists something amazing and disturbing. 3I Atlas probably formed in conditions completely different from anything in our solar system. It grew up around a different star, where the rules were nothing like what we have here. The discoveries kept getting stranger. 3I Atlas started releasing water vapor when it was still incredibly far from the sun. The comet was way out near Jupiter's orbit, about 3.5 astronomical units from the sun. That's 3.5 times farther from the sun than Earth is. At that distance, the sun's heat should be far too weak to melt much ice. Solar radiation should barely penetrate the comet's frozen surface. Yet instruments on Earth and in space detected clear signs of water molecules breaking apart into hydrogen and oxygen. Something was heating the inside of the comet before the sun's energy should have been strong enough to cause this effect. Even more disturbing, recent observations detected what appears to be a jet of material pointing toward the sun instead of away from it. This violates every principle of comet physics that scientists have established over centuries of careful observation. It's like watching a river flow uphill or a ball roll up a slope on its own. The laws of physics say this shouldn't happen, Solar radiation pressure should push material away from the sun, not pull it toward the sun. Yet the observations suggest that 3I Atlas is doing exactly this impossible thing. Scientists keep changing their estimates about how big 3I Atlas actually is. When they first spotted it as a faint dot moving against the background stars, they thought it might be just a few hundred meters across. That would make it about the size of a large building. As they gathered better observations with more powerful telescopes, they revised their estimates upward. Now, they think it could be as large as 10 to 20 kilometers in diameter. That's not just a chunk of ice anymore. That's bigger than Mount Everest, carrying unknown chemistry and exhibiting unexplained behavior as it races toward our sun. The implications of all these strange observations started small in scientists' minds, but grew exponentially as more data came in. If this jet pointing towards the sun is real, if material from 3I Atlas is being directed sunward by some mechanism we don't understand, then we're not dealing with a passive chunk of ice following predictable physics. We're dealing with something that's actively interacting with our solar environment in ways that our theories don't explain and our models can't predict. The object will reach perihelion, which is the fancy scientific word for its closest approach to the sun, on October 29, 2025. At that point, 3I Atlas will be approximately 1.36 astronomical units from our star. That places it somewhere between the orbits of Earth and Mars. While that might sound like a safe distance, and in many ways it is, distance becomes much less important if 3I Atlas triggers a solar event that sends charged particles racing toward Earth at millions of miles per hour. Every day that passes brings 3I Atlas about 1.4 million kilometers closer to its appointment with our sun. The solar heating intensifies with each passing hour. The rate at which the comet releases gases increases steadily. That mysterious sunward jet, if it's real, is becoming more active. Scientists around the world are running out of time to understand what they're really dealing with before the comet plunges into the intense radiation and magnetic field environment near the sun. Chapter 2: Understanding Our Sun. Before we can understand what 3I Atlas might do when it gets close to the sun, we need to understand what the sun actually is. The sun might look like a peaceful ball of golden light in the sky, but it's actually one of the most violent and energetic places in our entire solar system. The sun is a massive sphere of superhot gas, mostly hydrogen and helium, held together by its own enormous gravity. Deep inside the sun's core, temperatures reach about 15 million degrees Celsius. At these incredible temperatures, hydrogen atoms smash together with such force that they fuse into helium atoms. This process, called nuclear fusion, releases tremendous amounts of energy. This energy slowly works its way outward from the core, taking thousands of years to reach the surface. When it finally escapes, it radiates out into space as light and heat that makes life possible on Earth. The sun's surface isn't smooth and calm like it appears when you look at it during sunset. It roils and churns like water boiling in a pot. Huge bubbles of hot gas, each one bigger than Earth, rise up from below. When they reach the surface, they cool off slightly and sink back down. This constant churning motion creates patterns that scientists can see with special telescopes that protect their eyes from the sun's intense light. The surface temperature reaches about 5,500 degrees Celsius, which is hot enough to instantly melt any known material. But here's where things get really strange. Above the visible surface of the sun lies a region called the corona. The corona is made of extremely thin gas that's incredibly hot. While the sun's surface is only about 5,500 degrees, the corona reaches temperatures over 1 million degrees Celsius. Scientists still don't completely understand why the corona is so much hotter than the surface below it. How can the atmosphere be hotter than the thing heating it? This mystery remains one of the biggest unsolved problems in solar physics. The sun doesn't shine with perfectly steady light, like a light bulb. It has storms and eruptions that release enormous amounts of energy into space. Solar flares are sudden bursts of energy that brighten part of the sun for minutes or hours. These flares happen when magnetic field lines near the sun's surface become twisted and stressed. Suddenly, they snap and reconnect in a different pattern, releasing energy. A single large solar flare can release as much energy as billions of nuclear bombs exploding at once. Coronal mass ejections, or CMEs, are even more dramatic than solar flares. These events happen when the sun's magnetic field becomes so twisted and stressed that it can't hold itself together anymore. The field snaps violently and releases, throwing billions of tons of solar material out into space like a giant explosion. These clouds of electrically charged particles fly away from the sun at speeds over 1 million kilometers per hour, carrying both matter and magnetic fields with them. When these clouds of charged particles hit Earth, they interact with our planet's magnetic field in complex ways. This interaction can create beautiful auroras, those shimmering curtains of green, red, and purple light that dance across the sky near the North and South Poles. People travel thousands of miles to see auroras because they're so beautiful. But strong solar storms can also cause serious problems. They can damage satellites that orbit Earth. They can disrupt radio communications that ships and airplanes depend on. They can even cause problems with power grids on the ground, potentially causing blackouts that affect millions of people. The sun goes through a cycle of activity that repeats about every 11 years. During solar minimum, the sun is relatively calm and peaceful. It has few sunspots, which are those dark spots that appear on the sun's surface. During solar minimum, the sun produces fewer flares and coronal mass ejections. Everything is quieter. But during solar maximum, the sun becomes much more active and energetic. Sunspots appear frequently all over the sun's surface. Solar flares and eruptions happen much more often. The whole sun seems angrier and more violent. Scientists track this 11-year cycle by counting sunspots and monitoring solar activity with telescopes and satellites. Right now, we're approaching solar maximum in what scientists call solar cycle 25. This means the sun is becoming more active with each passing month. More sunspots are appearing, more flares are erupting, more coronal mass ejections are blasting material into space. This is completely normal and natural. The sun has been doing this for billions of years, cycling between calm and active periods like clockwork. The timing of 3I Atlas's arrival during this active phase of the solar cycle has caught the attention of scientists who study the sun. It's like having a mysterious visitor show up at your house just when things are most likely to be chaotic and unpredictable. The comet will experience the sun at its most energetic, most violent, and most unpredictable state. Nobody knows exactly what will happen when these two things come together. Earth orbits at exactly the right distance from the sun for life to exist. We receive enough warmth and light for water to stay liquid and for plants to grow through photosynthesis. But we also need protection from the sun's more dangerous side, from all that radiation and those streams of charged particles constantly flowing away from the sun. Fortunately, Earth has a magnetic field that acts like an invisible shield. Deep inside our planet, about 3,000 kilometers below the surface, liquid iron flows and swirls in the outer core. The motion of this conducting liquid creates electric currents, and these electric currents generate a magnetic field. This field extends far out into space, creating a protective bubble called the magnetosphere that surrounds our entire planet. The magnetosphere deflects most of the dangerous particles that stream from the sun. Without this protection, solar radiation would gradually strip away our atmosphere, the way it has stripped away most of Mars's atmosphere. Earth would become a barren, lifeless rock like Mars is today. The magnetic field is one of the main reasons Earth can support life while Mars cannot. The sun's energy drives our weather and creates our seasons. It powers the water cycle that brings rain. It enables photosynthesis in plants, which forms the base of the entire food chain. Every plant, animal, and person on Earth depends on energy that originally came from the sun. But that same energy source occasionally sends storms our way that test the limits of our technology and our magnetic shield. Scientists who study space weather watch the sun constantly, the same way meteorologists watch storms on Earth. They use satellites positioned between Earth and the sun to monitor solar activity. When they see a large coronal mass ejection heading toward Earth, they can measure how fast it's moving and predict when it will arrive. This gives them time to warn power companies, satellite operators, airlines, and other groups that might be affected. Usually we get several hours or even a few days of warning before a solar storm reaches Earth. This prediction and warning system is one of humanity's best defenses against space weather. We can't prevent solar storms, but we can prepare for them. Power companies can adjust how their grids operate to protect sensitive equipment. Satellite operators can put their spacecraft into safe modes that reduce vulnerability to radiation. Airlines can reroute flights away from polar regions where radiation exposure is highest during solar storms. All of this preparation helps minimize the damage that solar storms can cause. Chapter 3: The Science of Studying Space Visitors. Studying an object like 3I Atlas that's millions of kilometers away requires some of the most advanced technology humans have ever created. Scientists can't travel to the comet to examine it up close. They can't bring samples back to Earth to study in laboratories. Instead, they have to use telescopes and other instruments to gather information from a distance. It's like being a detective who has to solve a mystery without ever visiting the crime scene. Scientists use several different types of telescopes, and each one has special abilities that help answer different questions. The James Webb Space Telescope floats in space about 1.5 million kilometers from Earth. It looks at infrared light, which is a type of light that human eyes can't see. Infrared light is basically heat radiation. By detecting infrared light from 3I Atlas, scientists can measure the comet's temperature and figure out what chemicals it's releasing into space. The Hubble Space Telescope, which has been orbiting Earth since 1990, takes incredibly detailed pictures in visible light and ultraviolet light. These pictures show the structure and shape of comets. Scientists can see if a comet is round or lumpy. They can watch for jets of gas shooting out from specific spots on the surface. They can measure how bright the comet gets as it approaches the sun. All of this information helps them understand what's happening to the comet. On the ground, huge telescopes in places like Chile, Hawaii, and other locations with clear, dark skies track where objects move through the solar system. These telescopes can't see quite as much detail as space telescopes, because Earth's atmosphere gets in the way. But ground-based telescopes are much larger and can collect more light. They're also easier to upgrade and repair than telescopes in space. These different telescopes work together like a team of detectives sharing clues. Each one provides a different piece of the puzzle. The James Webb Space Telescope tells scientists what chemicals the comet contains. The Hubble Space Telescope shows them the comet's structure. Ground-based telescopes track its motion and brightness. When scientists combine all this data, they can build a complete picture of what 3I Atlas is and how it's behaving. The most important tool for studying what comets are made of is called spectroscopy. This might sound like a complicated word, but the basic idea is actually pretty simple. When light bounces off an object or passes through gas, different chemicals affect the light in different ways. It's similar to how a prism splits white sunlight into a rainbow of colors. Every chemical element and molecule creates a unique pattern in light, almost like a fingerprint that identifies it. Hydrogen creates one pattern. Oxygen creates a different pattern. Carbon dioxide creates its own unique pattern. Water vapor has its own fingerprint. Scientists can look at the light coming from 3I Atlas, split it into all its different colors, and identify exactly which chemicals are present based on these fingerprints. For 3I Atlas, spectroscopy revealed something shocking. The fingerprints in the light showed huge amounts of carbon dioxide. Scientists saw the characteristic pattern of CO2 molecules everywhere in the gas surrounding the comet. They also saw water vapor, but much less than they expected. This backward ratio, with more carbon dioxide than water, puzzled astronomers because every comet from our solar system has the opposite pattern. The chemicals that a comet releases tell scientists the story of where it formed and what it experienced during its life. Water ice forms easily in cold regions of space, where temperatures drop below -100 degrees Celsius. Carbon dioxide can also freeze into ice, but it sublimates turns from solid to gas at slightly warmer temperatures than water ice. The fact that 3I Atlas has so much carbon dioxide suggests it formed in a place where carbon dioxide ice was more stable and common than water ice. This tells scientists something important about the star system where this comet was born. That system must have had different conditions than our solar system. Maybe the star was a different type than our sun. Maybe the region where comets formed was at a different temperature. Maybe the chemical makeup of the cloud that formed the star system was different. Every detail about 3I Atlas's chemistry provides clues about its distant home. Figuring out exactly where 3I Atlas came from and where it's going requires careful mathematical calculations that would take humans years to do by hand. Fortunately, we have powerful computers that can handle the complex math. Scientists take pictures of the comet on different nights and measure how its position changes against the background stars. From these measurements, they calculate the comet's orbit. This orbital calculation is more complicated than it might seem. The math has to account for gravity from the sun, from all the planets, and even from large asteroids. Everything in the solar system pulls on everything else with its gravity. Jupiter, being huge, has strong gravity that affects the paths of comets and asteroids. Saturn, Uranus, and Neptune also tug on passing objects. Even Earth's small gravity has a tiny effect. Modern computers can handle all these gravitational interactions and predict where an object will be months or years into the future. For 3I Atlas, these calculations revealed something special and rare. The comet's path is open rather than closed. To understand what this means, Think about the difference between a circle and a curve that never loops back on itself. Planets follow circles or shapes close to circles around the sun. They're trapped by the sun's gravity and will orbit forever, or at least for billions of years until the sun dies. But 3I Atlas follows that open curve called a hyperbola. It came from interstellar space at high speed. It will swing past the sun once, and then it will leave our solar system and never return. The comet's speed is too great for the sun's gravity to capture it into an orbit. This proves beyond any doubt that 3I Atlas came from another star system. It's not just an unusual comet from the outer parts of our solar system. It's truly an interstellar visitor. Scientists can even trace the comet's path backward in time to figure out roughly which direction it came from. The calculations show that 3I Atlas came from a direction in the sky that contains many stars. Without knowing more details, it's impossible to say exactly which star system ejected this comet billions of years ago. But we know it traveled for an incredibly long time through the cold, dark space between stars before finally entering our solar system. After months of careful observations and calculations, scientists have built up a detailed file on 3I Atlas. They know its size, its speed, its chemical composition, and its path through the solar system. They've created computer models that try to explain its unusual behavior. They've compared it to every other comet in their extensive databases. Some things about 3I Atlas match what scientists expected based on comet theory. It releases gases as it gets closer to the sun, which is normal. It reflects sunlight in ways that make sense for an icy object covered in dark dust. Its orbit follows the laws of gravity perfectly, with no violations of Newton's laws or Einstein's general relativity. But other aspects of 3I Atlas remain deeply mysterious and troubling. That strange chemical composition with too much carbon dioxide doesn't match any formation model for comets in our solar system. The early release of water vapor at huge distances from the sun, way out near Jupiter's orbit, doesn't fit normal models of how solar heating affects comets. The possible jet of material pointing toward the sun, rather than away from it, would violate basic principles of physics that have held true for every comet ever studied. These mysteries haven't been solved yet. Scientists continue gathering new data every night when the comet is visible from their telescopes. They're hoping that more observations will either explain away the anomalies or confirm that 3I Atlas truly is unlike anything we've encountered before. The clock is ticking down toward perihelion, when the comet will reach its closest approach to the sun and either confirm our worst fears or provide the answers scientists desperately need. Chapter 4: What could go wrong? Now we need to talk about the possibilities that worry scientists the most. While most experts think 3I Atlas will pass by without causing major problems, they can't completely rule out scenarios where the comet's unusual properties trigger events that affect Earth. Understanding these possibilities helps us prepare, and also helps us understand why scientists take interstellar visitors so seriously. The biggest concern involves the possibility that 3I Atlas could somehow trigger enhanced solar activity. The sun already produces flares and coronal mass ejections naturally as part of its normal behavior. But scientists wonder whether adding exotic materials from 3I Atlas into the mix could change how the sun behaves, like adding a chemical to a fire that makes it burn hotter or in a different color. Here's how this triggering mechanism might work. As 3I Atlas approaches the sun, it releases gases at an increasing rate due to solar heating. These gases contain carbon dioxide, water vapor, and possibly other chemicals we haven't identified yet. Some of these molecules break apart under intense solar radiation, creating individual atoms and electrically charged particles called ions. These particles mix into the solar wind, that constant stream of particles flowing away from the sun at hundreds of kilometers per second. The solar wind isn't uniform like water from a hose. It's more like a turbulent river with swirls, currents, and variations in speed and density. When particles from 3I Atlas enter this complex flow, they could potentially affect how the sun's magnetic field behaves. The sun's magnetic field is incredibly complicated, with loops and tangles and regions of intense field strength. Sometimes these magnetic structures become so stressed and twisted that they suddenly release their stored energy in violent events. If particles from 3I Atlas change the properties of the solar wind even slightly, they might affect how magnetic energy builds up and releases in the solar corona. Small changes in the trigger conditions could potentially lead to larger eruptions than would occur naturally. This is what worries some scientists, though most think the effect would be minimal or non-existent. A really strong solar storm could potentially cause serious problems for our technology-dependent civilization. The most famous historical example is the Carrington event of 1859. On September 1st of that year, astronomers observed large sunspots on the sun. The next day, they saw a massive solar flare erupt. About 18 hours later, a coronal mass ejection from that flare slammed into Earth's magnetic field. The results were spectacular and frightening. Auroras appeared as far south as the Caribbean and Hawaii, places where they're almost never seen. The auroras were so bright that people could read newspapers by their light in the middle of the night. Telegraph systems around the world went haywire. Some telegraph operators received electric shocks from their equipment. Telegraph papers caught fire. Some operators found they could send messages even after disconnecting their batteries because the induced currents from the storm provided enough power. Back in 1859, telegraphs represented the most advanced technology humans had. There were no power grids connecting cities. There were no satellites. There were no computers or internet. The total economic impact of the Carrington event was measured in thousands of dollars, and it mainly affected telegraph communication. If a storm of the same intensity happened today, the effects would be catastrophically different. The National Academy of Sciences did a study estimating the impacts of a Carrington-level event in the modern world. They concluded it could leave 130 million Americans without electrical power for months. It could disable GPS satellites that provide navigation and timing services that modern civilization depends on. It could cause trillions of dollars in damage to our interconnected technological systems. But these disaster scenarios assume natural solar variability, following patterns we understand based on historical records and solar physics models. None of them account for the possibility that an external trigger, especially one carrying unknown chemistry from another star system, might amplify or accelerate solar storms beyond what our models predict. The power grid represents one of our most vulnerable systems. Modern electrical grids are designed for high efficiency, which unfortunately makes them more fragile. Long power lines act like giant antennas that can pick up electromagnetic disturbances. During a severe geomagnetic storm, these power lines experience induced currents, essentially electricity generated by the changing magnetic fields. These induced currents can overload transformers, the large devices that step voltage up and down for efficient power transmission. Large transformers are custom built for specific locations. They're expensive, costing millions of dollars each. Worse, manufacturing a replacement transformer takes 12 to 18 months because they're so complex and specialized. If a major geomagnetic storm damaged hundreds of transformers simultaneously across a continent, replacing them all would take years. During that time, millions of people would be without reliable electrical power. The satellite systems that modern life depends on face direct exposure to enhanced radiation during solar storms. Over 5,000 active satellites currently orbit Earth, providing weather monitoring, communications, GPS navigation, and countless other services. These spacecraft operate in regions of space where Earth's magnetic field traps charged particles from the sun. During normal conditions, these radiation belts contain manageable levels of particles. But during severe geomagnetic storms, particle levels spike dramatically. Satellites are designed with radiation shielding appropriate for normal space weather conditions. The shielding protects sensitive electronics from the constant low-level radiation they experience every day. But this shielding might not be adequate for the extreme conditions during a severe solar storm, especially if 3I Atlas somehow amplifies the storm beyond historical levels. When high-energy particles slam into satellite electronics, they can cause various problems. Some effects are temporary, like computer glitches that reset systems but don't cause permanent damage. But sustained exposure to high radiation levels can permanently degrade electronic components, eventually causing satellites to malfunction or fail completely. The replacement cost for a large satellite can exceed $500 million, and building and launching a replacement takes years. The GPS constellation represents a particularly critical vulnerability. These 31 satellites provide positioning and timing data that modern civilization cannot function without. GPS gives us navigation in our cars and phones, but that's just the beginning. Power grids use GPS timing signals to synchronize electrical transmission across vast distances. Financial markets use GPS timestamps to order transactions and prevent market manipulation. Cell phone towers use GPS to coordinate their signals. Emergency services depend on GPS coordinates for dispatching help. If a major solar storm disabled even a portion of the GPS constellation, the effects would cascade through every sector of modern life. Aircraft would lose precision navigation capability, potentially forcing flight cancellations. Shipping containers would become difficult to track, disrupting global supply chains. ATM networks might fail as banks lose the ability to synchronize transactions. Even cellular phone networks could degrade as cell towers lose their timing references. The internet infrastructure faces vulnerabilities through multiple pathways. Fiber optic cables themselves are immune to electromagnetic interference because they transmit information as light pulses rather than electrical signals. However, these cables depend on electronic equipment at regular intervals to amplify and route signals. This equipment could be damaged by induced currents during a geomagnetic storm. Undersea cables that connect continents are particularly vulnerable. These cables cross thousands of kilometers of ocean, using electronic repeaters every 50 to 100 kilometers to amplify the weakening signals. These repeaters sit on the ocean floor, impossible to access quickly for repairs. If many repeaters were damaged simultaneously, it could fragment global internet connectivity for months, while new cables are manufactured and laid. Some people worry about biological effects from solar storms or from exotic materials that 3I Atlas might carry. The good news is that Earth's atmosphere and magnetic field protect us very effectively from space radiation. Even during severe solar storms, people on the ground experience no direct harmful radiation. The atmosphere absorbs particles and radiation before they reach the surface. The one exception involves airplane passengers and crew, especially on polar routes. Radiation exposure is higher at airplane altitudes than on the ground, and highest near the poles, where Earth's magnetic field provides less shielding. During major solar storms, airlines can reroute flights away from polar regions to reduce passenger radiation exposure. This is a routine precaution that's been used many times without any reported health effects. The possibility of biological contamination from 3I Atlas is extremely unlikely, but worth mentioning because some people worry about it. The theory of panspermia suggests that life might spread between star systems via comets and asteroids. If microorganisms could survive the journey through interstellar space, they might seed new planets with life when comets impact those planets. Laboratory experiments have shown that certain extremely tough microorganisms called extremophiles can survive exposure to space conditions for limited periods. Tardigrades, those microscopic creatures that look like eight-legged bears under a microscope, can enter a state of suspended animation where their metabolism essentially stops. In this state, they can survive radiation, vacuum, and temperature extremes that would kill almost any other organism. But 3I Atlas has been traveling through space for millions of years, at minimum, possibly billions of years. During that entire journey, it's been exposed to cosmic radiation that's far more intense than the radiation near Earth. Even extremophiles would have difficulty surviving such prolonged exposure. Additionally, the comet won't come anywhere near Earth. It will pass between Earth and Mars, millions of kilometers away from our planet. There's no mechanism for material from 3I Atlas to reach Earth's surface. Even if the comet did somehow carry living organisms, and even if some of them survived the interstellar journey, and even if some material from the comet reached Earth, the material would have to survive entering our atmosphere. When objects fall through the atmosphere at high speed, friction heats them to thousands of degrees. This intense heat sterilizes any biological material. The chain of unlikely events required for biological contamination is so long that scientists consider it effectively impossible. The gravitational effects of 3I Atlas are another area where some people have concerns. Every object with mass generates gravity, and 3I Atlas has enough mass to create a small gravitational field. However, the comet's gravity is absolutely tiny compared to the Sun's gravity, or even Earth's gravity. At the distances involved, 3I Atlas's gravitational pull on Earth would be immeasurably small. To put this in perspective, the Moon orbits Earth at an average distance of about 384,000 kilometers. The Moon's gravity is strong enough to create tides in Earth's oceans, raising sea levels by several meters twice each day. 3I Atlas will pass no closer than about 200 million kilometers from Earth. At that distance, its gravitational effect would be millions of times weaker than the Moon's effect, far too small to detect, even with our most sensitive instruments. Some observations have suggested that 3I Atlas might be generating gravitational effects slightly stronger than its estimated mass would predict. This discrepancy is very small and might simply mean that our mass estimates are wrong. But if the gravitational anomaly is real, it could indicate that the comet contains unusual materials with exotic properties. This ventures into very speculative physics, involving hypothetical forms of matter that haven't been confirmed to exist. The timing of 3I Atlas's arrival during solar maximum is unfortunate, but probably just coincidence. The Sun's 11-year cycle is completely predictable. We always know, roughly, when solar maximum will occur. An interstellar object arriving during any randomly chosen 11-year period would have about a 50-50 chance of arriving during the more active half of the cycle. So it's not terribly surprising that 3I Atlas happens to be approaching perihelion when the Sun is becoming more active. That said, the coincidence does mean we're testing our theories and technologies during a time when the Sun is already producing more storms than usual. If 3I Atlas were arriving during solar minimum when the Sun is calm, any effects it might have would stand out clearly against a quiet background. Arriving during solar maximum means any effects could be masked by natural solar variability, or alternatively, they could combine with natural activity to create stronger storms than either cause would produce alone. Chapter 5. Why most scientists aren't panicking. After reading about all the things that could potentially go wrong, you might be wondering why scientists aren't more worried. The answer involves understanding probability, scale, and how science actually works. While scientists take 3I Atlas seriously and are studying it carefully, most don't think it will cause catastrophic problems. Let's explore why. First, space is unimaginably huge. Even though 3I Atlas is large for a comet, it's incredibly tiny compared to the Sun. The Sun contains 99.86% of all the mass in our entire solar system. The Sun is so large that over 1 million Earths could fit inside it. Compared to this giant ball of plasma, 3I Atlas is like a grain of sand next to a beach ball. The amount of material that 3I Atlas can release into space is minuscule compared to the vast volume of the solar wind. Even if the comet is releasing tons of gas every second, that material gets diluted into the huge volume of space around the Sun. It's like adding a few drops of food coloring to an entire swimming pool. The effect on the overall system is probably too small to matter. Scientists have studied many comets passing close to the Sun over the years. Some comets, called sun grazers, actually dive into the Sun's outer atmosphere before being destroyed. These comets release enormous amounts of material directly into the solar corona. Astronomers watch them carefully to see if they trigger solar activity. Sometimes sun grazers coincide with solar eruptions, but scientists generally think these are coincidences rather than cause and effect relationships. If comets that literally crash into the Sun don't trigger major solar storms, it seems unlikely that 3I Atlas, which will pass much farther away, would have a significant effect. The Sun is simply too large and too energetic to be strongly affected by such a small visitor, even one carrying unusual chemistry. The unusual chemical composition of 3I Atlas is scientifically interesting, but not necessarily threatening. The fact that the comet has more carbon dioxide than water tells us about its origin, not about any danger it poses. Carbon dioxide is a common molecule in space. Earth's neighbor Venus has an atmosphere made almost entirely of carbon dioxide. While the ratio is unusual for a comet, the chemicals themselves aren't exotic or dangerous. The early outgassing that 3I Atlas exhibited when it was still far from the Sun is puzzling, but not unprecedented. Some comets show surprising activity at large distances, possibly due to unusual internal composition or heat from radioactive materials in their interiors. Several explanations could account for this behavior without requiring us to invoke exotic physics or artificial mechanisms. The The possible jet pointing toward the sun is the observation that troubles scientists most because it would violate known physics. However, this observation hasn't been definitively confirmed. It's difficult to determine jet directions with absolute certainty from Earth-based observations. The apparent sunward jet might be an optical illusion, or a jet that's actually pointing in a different direction but appears sunward due to the viewing angle from Earth. Scientists deal with uncertainty by gathering more data and testing different explanations. They don't jump to dramatic conclusions based on preliminary observations. The scientific method requires careful verification before accepting claims that would overturn established physics. Until multiple independent teams confirm the sunward jet using different instruments and methods, most scientists remain cautiously skeptical. The history of astronomy includes many examples of observations that initially seemed to defy explanation but turned out to have natural causes. In the 1960s, astronomers discovered pulsars, objects that flashed radio waves with incredible regularity. Some scientists briefly wondered if they might be artificial beacons created by alien civilizations. Further study revealed they were actually rapidly spinning neutron stars, natural objects with properties no one had predicted. Nature is often stranger than our imaginations, but it still follows physical laws. Another reason scientists aren't panicking is that we've been through similar situations before. When the first interstellar object, Oumuamua, was discovered in 2017, some people worried it might be dangerous or artificial. It had an unusual shape and accelerated slightly as it left the solar system. Some researchers even suggested it might be an alien probe. But Oumuamua passed through our solar system without causing any problems. It didn't trigger solar storms. It didn't threaten Earth. It simply gave us new data about interstellar objects and then left. The second interstellar object, 2I Borisov, discovered in 2019, was even less concerning. It looked and acted like a normal comet, aside from its interstellar origin. It followed predictable physics. It didn't exhibit any particularly strange behaviors. Scientists studied it intensively and learned a lot about how comets form in other star systems, but it posed no threat. 3I Atlas is unusual compared to these previous visitors, which is why scientists are paying such close attention to it. But unusual doesn't automatically mean dangerous. The universe is full of diversity. Every new object we discover teaches us that nature is more varied and complex than our theories predicted. This is exciting for science, but it doesn't necessarily mean we're in danger. The warning systems we have in place provide another layer of protection. Space weather forecasters at organizations like NOAA's Space Weather Prediction Center monitor the sun 24 hours a day, 7 days a week. They have satellites positioned between Earth and the sun that can detect coronal mass ejections as soon as they erupt. These satellites measure the speed, density, and magnetic field of the approaching plasma cloud. From these measurements, forecasters can predict when the storm will reach Earth, usually with several hours to days of warning. They issue alerts to power companies, airlines, satellite operators, and other groups that might be affected. This warning time allows everyone to take protective measures. It's similar to how hurricane forecasters track storms and issue warnings before they make landfall, giving people time to prepare. Even if 3I Atlas did somehow trigger enhanced solar activity, we would see the results developing and have time to respond. Solar storms don't appear instantly. Coronal mass ejections take hours to build up and erupt. Then they take additional hours or days to cross the 150 million kilometers between the Sun and Earth. Throughout this time, our satellites and instruments would be monitoring the situation and providing updates. The media tends to sensationalize scientific discoveries, especially ones involving space and potential threats. Headlines designed to get clicks often make things sound more dramatic or scary than they actually are. When you see headlines about 3i Atlas, it's important to look at what the actual scientists are saying, not just what news sites put in their headlines to attract attention. Most peer-reviewed scientific papers about 3i Atlas focus on its scientific interest rather than potential threats. Researchers are excited about the opportunity to study an interstellar object with unusual properties. They're gathering data that will teach us about other star systems. They're testing theories about comet formation and behavior. This is what scientists do when they encounter something new and interesting. They study it carefully to understand it better. The absence of major warnings from space agencies like NASA and ESA also tells us something important. These organizations have protocols for assessing and communicating threats from space. If 3i Atlas posed a serious danger to Earth or our technology, these agencies would be issuing clear public warnings and coordinating international responses. The fact that they're treating this as a scientific opportunity rather than a planetary emergency suggests that experts who have access to all the data aren't particularly worried. That doesn't mean we should ignore 3i Atlas or stop studying it. Scientists will continue observing the comet intensively as it approaches perihelion. They'll watch for any signs of unusual interactions with the sun. If something unexpected starts happening, they'll alert the appropriate authorities and the public. But right now, based on all available evidence, most experts think the most likely outcome is that 3i Atlas will pass through perihelion, provide us with fascinating scientific data, and then continue its journey back into interstellar space without causing major problems. Understanding the difference between "this is unusual and scientifically interesting" and "this is dangerous and threatening" is important for staying informed without becoming unnecessarily anxious. Science thrives on discovering unusual things that challenge our understanding. That's how we learn and grow. But unusual doesn't equal dangerous. Most of the time, it just equals interesting. Chapter 6. Preparing sensibly. Now that we understand both the possibilities and the probabilities, let's talk about what reasonable preparation looks like. The key is finding a balance between being completely unprepared and becoming overly anxious about unlikely scenarios. For most people, especially students and families without special responsibilities, no special preparation is needed for 3i Atlas specifically. The comet will either pass by without incident, or if it does trigger any solar activity, the warning systems in place will alert authorities who can take appropriate measures. Your regular emergency preparedness that makes sense for local disasters like storms or earthquakes is sufficient. However, this is a good opportunity to learn about general emergency preparedness. Every family should have some basic emergency supplies, regardless of what happens with 3i Atlas. Having a few days' worth of food, water, batteries, and other basics makes sense for any situation where services might be disrupted temporarily. This isn't about 3i Atlas specifically. This is just smart planning that helps you deal with power outages, severe weather, or other local emergencies. A basic emergency kit should include water, 1 gallon per person per day for at least 3 days, non-perishable food that doesn't require cooking, a battery-powered or hand-crank radio for getting information if the power is out, flashlights with extra batteries, a first aid kit, any prescription medications your family needs, and basic sanitation supplies. Many families already have most of these items around their house. It's just a matter of organizing them in one place, where you can find them quickly if needed. If you're interested in following the science of 3-Eye Atlas, there are many great resources online. NASA's website has regular updates about the comet. Many observatories share their latest images and findings. Science news sites like space.com and Sky and Telescope report on new discoveries. Following these sources lets you learn about the comet as scientists learn more, without getting drawn into sensationalized or speculative content. For students, this is an excellent learning opportunity. You're witnessing real science in action. Scientists are making observations, forming hypotheses, testing predictions, and revising their understanding based on new data. This is exactly how the scientific method works. You can follow along and see how scientists deal with uncertainty and how they communicate findings to each other and to the public. You might even be able to observe 3-Eye Atlas yourself if you have access to binoculars or a small telescope. As the comet gets closer to the sun, it will likely brighten enough to see with optical aids, possibly even with the naked eye if it becomes very active. Astronomy clubs and planetariums in your area might hold special viewing events. Seeing an interstellar visitor with your own eyes would be an amazing experience you could remember for the rest of your life. If you do feel anxious about 3-Eye Atlas or space threats in general, that's a normal human reaction. Our brains evolved to pay extra attention to potential dangers, which helped our ancestors survive. But in the modern world, this can make us worry too much about unlikely events while ignoring more probable risks. Talking about your concerns can help. Parents, teachers, or school counselors can provide perspective and reassurance. Learning more about the actual science often reduces anxiety because you understand what's really happening, rather than imagining worst-case scenarios. Knowledge is one of the best remedies for fear. It's also important to limit exposure to sensationalized content. Some websites and social media accounts thrive on creating fear and anxiety because it keeps people coming back to check for updates. If you find yourself constantly checking for news about 3-Eye Atlas and feeling more anxious each time, it's okay to step back and focus on other things. The comet will do whatever it's going to do, regardless of how much we worry about it. Remember that scientists and engineers around the world are working to protect our technology and understand space weather risks. These experts have spent their entire careers studying these problems. They have plans and procedures in place. Power companies know how to protect their equipment during solar storms. Satellite operators know how to put spacecraft in safe modes. Emergency management agencies have response protocols. You can trust that many smart, dedicated people are handling the technical aspects of monitoring and responding to any space weather events. For people who work in critical infrastructure like power companies, telecommunications, or emergency services, your organizations probably already have space weather response plans. These plans were developed based on scientific understanding of solar storms, not specifically because of 3-Eye Atlas. Following your organization's established procedures is the appropriate response, regardless of whether solar storms are naturally occurring or potentially enhanced by the comet. Chapter 7. What happens next? As October 29th approaches, the intensity of scientific observation increases. Every major telescope that can see 3-Eye Atlas is gathering data. Scientists are taking measurements constantly, building up the most complete data set ever collected for an interstellar object approaching the sun. This information will be valuable for decades to come, helping astronomers understand these rare visitors. The comet is getting brighter as it approaches the sun, which makes it easier to study, but also means it's heating up and becoming more active. The rate at which it releases gases is increasing steadily. Any jets or outbursts are becoming more pronounced. Scientists can see more details in their observations as the comet's activity intensifies under the sun's growing heat and radiation. In the final days before perihelion, 3I Atlas will pass into a region of sky very close to the sun as seen from Earth. This makes observation difficult because telescopes can't point too close to the sun without risking damage to sensitive instruments. There will be a period of several days when we can't directly observe the comet because it's lost in the sun's glare. This observational gap is frustrating for scientists, but unavoidable. During this time, they'll rely on satellites that can block out the sun's light to observe the region around it. These instruments can track the comet even when ground-based telescopes cannot. However, the resolution and detail won't be as good as what large ground-based telescopes provide. When 3I Atlas emerges from behind the sun and becomes visible again, scientists will immediately examine it for any changes. Did it brighten more than expected? Did it split into pieces? Is it releasing more or different gases than before perihelion? Every detail will be compared to predictions to see how well our models performed. The days and weeks after perihelion are crucial for understanding whether 3I Atlas had any effect on solar activity. Scientists will analyze solar data looking for any anomalies that coincide with the comet's closest approach. They'll compare solar behavior during this period to what normally happens during solar maximum. Any differences might indicate that the comet influenced the sun, though proving cause and effect is difficult when dealing with a system as complex as the sun. If 3I Atlas passes through perihelion without triggering any unusual solar activity, that will be an important scientific result in itself. It will tell us that even comets with unusual chemistry don't significantly affect solar behavior. This would support the view that the sun is too large and powerful to be strongly influenced by small visitors, no matter how exotic they might be. If unusual solar activity does occur around the time of perihelion, scientists will have to carefully analyze whether it was caused by 3I Atlas or was simply a coincidence. The sun is approaching solar maximum and producing storms frequently. Proving that a particular storm was triggered by the comet rather than occurring naturally would require detailed analysis of timing, location, and physical mechanisms. After perihelion, 3I Atlas will begin its journey back out of the solar system. It will pass Mars's orbit again, then Jupiter's orbit, gradually becoming fainter and harder to observe as it moves away from the sun. Eventually, months or years from now, it will become too faint for even our largest telescopes to detect. It will disappear back into the darkness between stars, perhaps to pass through another star system millions of years from now. The scientific papers analyzing 3I Atlas will continue for years after the comet itself has left our view. Researchers will study the data collected during its passage, testing theories and refining models. The information gathered will inform how we think about interstellar objects, comet formation in other star systems, and the diversity of conditions that exist around different types of stars. The lessons learned from 3I Atlas will also help us prepare for future interstellar visitors. As our detection capabilities improve, we'll discover more of these objects. Some might be even more unusual than 3I Atlas. Each discovery will teach us something new and challenge our understanding in different ways. This is how science progresses, through a series of observations and insights that gradually expand our knowledge. Future space missions might be designed to intercept and study interstellar visitors up close. Imagine a spacecraft that could rendezvous with an object like 3i Atlas, land on its surface, and collect samples to bring back to Earth. This might sound like science fiction, but engineers are already designing mission concepts for exactly this purpose. Within your lifetime, we might have pieces of other star systems sitting in laboratories here on Earth. The discovery and study of 3i Atlas represents humanity taking another step in understanding our place in the galaxy. We're no longer confined to studying objects that formed in our own solar system. We can now detect and analyze visitors from other stellar neighborhoods, learning about places so distant we'll never visit them with spacecraft. This is remarkable when you think about it. Chapter 8. The Bigger Picture. The story of 3i Atlas is part of a much larger story about humanity's relationship with the cosmos. For most of human history, the night sky was mysterious and unreachable. Ancient peoples created myths about the stars and planets, not understanding that they were physical objects, following natural laws. The idea that we could study the universe scientifically would have seemed impossible to them. The scientific revolution changed everything. When Galileo pointed his telescope at the sky in 1609, he saw mountains on the moon, moons orbiting Jupiter, and countless stars invisible to the naked eye. This was the beginning of modern astronomy. Over the following centuries, we learned that Earth orbits the Sun, that stars are distant suns, that our galaxy contains billions of stars, and that the universe contains billions of galaxies. Each discovery expanded our cosmic perspective. We learned that Earth isn't the center of the universe. We learned that our Sun is just one ordinary star among countless others. We learned that the universe is billions of years old and unimaginably vast. Each step humbled us by showing how small we are, but also empowered us by demonstrating that we can understand the cosmos through observation and reason. The discovery of planets orbiting other stars, which began in the 1990s, was another revolutionary step. We now know that planets are common in the galaxy. Most stars probably have planets. Some of these planets are rocky worlds like Earth. Some orbit at the right distance from their stars to potentially have liquid water on their surfaces. The possibility of life elsewhere in the universe has gone from pure speculation to a serious scientific question. Interstellar objects like 3i Atlas add another dimension to our cosmic knowledge. They're physical messengers from other star systems, carrying information about places we cannot visit. Every interstellar visitor tells us something about the diversity of conditions that exist around other stars. They show us that solar systems differ from each other in countless ways, and that objects travel between stars, connecting different systems in a vast galactic network. This growing understanding of the universe has practical implications beyond just satisfying curiosity. Studying other solar systems helps us understand our own better. We learn what's normal and what's special about our cosmic neighborhood. This knowledge aids in understanding Earth's climate, geology, and the conditions that allow life to exist. Space weather research, driven by concerns about solar storms, has led to better understanding of how the sun works. This understanding helps us protect our technology, but it also teaches us about stars in general. Every star in the galaxy operates on similar principles. By studying our sun in detail, we learn about the billions of other stars that are too distant to observe closely. The technologies developed for astronomy have applications far beyond studying space. CCD cameras, originally developed for telescopes, are now in every smartphone. GPS satellites were launched for navigation, but now provide timing signals essential for modern technology. Computer algorithms designed to process telescope data help analyze medical images. Science and technology form a connected web where advances in one area enable progress in others. The story of 3i Atlas also illustrates how science deals with uncertainty. Scientists don't have all the answers, and they're honest about this. When they encounter something new and unexpected, they admit they don't fully understand it yet. They gather more data, propose explanations, and test those explanations against observations. This process takes time, and it doesn't always produce immediate, definitive answers. This uncertainty makes some people uncomfortable. In our daily lives, we're used to getting quick answers to questions. You can look up facts on the internet instantly, but science doesn't work that way, especially when dealing with unprecedented phenomena. Scientific understanding develops gradually as evidence accumulates. This slower, more careful approach produces reliable knowledge that stands the test of time. Learning to be comfortable with uncertainty is a valuable life skill. Not everything has a clear answer. Some questions require more investigation before we can answer them confidently. Some problems have multiple possible solutions, and we need more information to determine which is correct. The ability to say, "I don't know yet, but I'm working on finding out," is a sign of intellectual honesty, not weakness. The collaborative nature of modern science is another important aspect of the 3i Atlas story. Astronomers around the world are sharing data about the comet. Researchers at different institutions analyze the observations using different techniques. They publish their findings in peer-reviewed journals where other scientists can evaluate and critique their work. This collaborative, open process helps ensure that errors are caught and that conclusions are supported by evidence. International cooperation in science transcends political boundaries. Scientists from different countries work together on projects like studying 3i Atlas because the questions they're asking are universal. The comet doesn't belong to any one nation. It's a visitor to our entire solar system. Understanding it benefits all of humanity, regardless of where individual researchers happen to live. This spirit of international cooperation in science offers a model for how humans might address other global challenges. Climate change, pandemic diseases, and resource management all require cooperation across borders. The scientific community shows that such cooperation is possible when people focus on shared goals and evidence-based reasoning rather than political divisions. The inspiration that space exploration provides shouldn't be underestimated either. Learning about 3i Atlas might inspire some students to pursue careers in science, technology, engineering, or mathematics. Even students who don't become scientists benefit from understanding how science works and why it matters. An educated public that understands scientific thinking is better equipped to make informed decisions about technology, policy, and the challenges facing society. Looking to the future, humanity's relationship with space will only grow stronger. We're developing new technologies that will enable deeper exploration. Better telescopes will discover more interstellar visitors and distant planets. Spacecraft will travel to new destinations in our solar system, and perhaps beyond. Each generation has the opportunity to push the boundaries of human knowledge and capability a bit further. You're living at a special time in history. You're part of the first generation growing up with the confirmed knowledge that interstellar objects visit our solar system. Your grandparents didn't know this. It was only discovered 8 years ago. You're witnessing scientific discoveries in real time that expand human understanding of the universe. This is a privilege that comes with the responsibility to learn, think critically, and perhaps contribute to this growing body of knowledge in your own way. The universe is vast, ancient, and full of wonders we're only beginning to discover. 3i Atlas is just one small part of this enormous cosmic story, but it's a part you can follow and learn from. Whether the comet turns out to be completely normal or reveals something surprising, studying it teaches us about the nature of reality and our place within it. And that's what makes science exciting. There's always something new to discover, always another mystery waiting to be solved. Chapter 9: The Final Approach. As I write these words, 3i Atlas continues its relentless journey toward the Sun. Each day brings it roughly 1.4 million kilometers closer to perihelion. The comet is now visible through large amateur telescopes as a faint, fuzzy spot moving slowly against the background stars. Professional astronomers are tracking it constantly, gathering data with every observation. The comet's brightness has been increasing as expected as it approaches the Sun. This brightening comes from increased outgassing as solar heating intensifies. More ice is sublimating from solid to gas, creating a larger cloud of material around the comet's nucleus. This cloud, called the coma, makes the comet appear bigger and brighter, even though the solid nucleus at the center hasn't changed size. Spectroscopic observations continue to show that unusual chemical signature with too much carbon dioxide and too little water compared to normal comets. Scientists have proposed various explanations for this chemistry. Perhaps 3i Atlas formed in a part of its home solar system that was slightly warmer than where our comets formed, causing more water ice to sublimate away early in its history. Perhaps the star it formed around had a different chemical composition that favored carbon dioxide formation over water. Some researchers have suggested that 3i Atlas might have lost water preferentially during its long journey through interstellar space. Cosmic radiation can break apart water molecules, allowing the hydrogen to escape into space, while heavier elements remain behind. Over millions of years, this could alter the comet's chemistry. However, this process should affect carbon dioxide similarly, so it doesn't fully explain the observed ratios. The possible sunward jet remains controversial. Some observation teams report seeing evidence of material flowing toward the Sun, while others see more ambiguous structures that could be interpreted differently. Part of the challenge is that we're viewing the comet from a specific angle from Earth. Jets that point in certain directions might create optical effects that make them appear to point sunward when they're actually aimed in other directions. To resolve this controversy, scientists would need observations from multiple viewing angles. Unfortunately, we don't have spacecraft near 3i Atlas that could provide these alternative perspectives. All our observations come from Earth, or from satellites orbiting Earth, which means we're all viewing the comet from roughly the same direction. Future missions to intercept interstellar visitors would solve this problem, but for now, we're limited to what we can see from our single vantage point. The magnetic field observations that some researchers claim to detect around 3i Atlas add another layer of mystery. Natural comets don't generate strong magnetic fields. They're made of ice and rock, neither of which is magnetic. If 3i Atlas does have a detectable magnetic field, it would suggest either unusual composition including magnetic minerals, or possibly even more exotic explanations. However, these magnetic field measurements are at the limit of what current instruments can detect. The signals are weak and noisy. Different research groups analyzing the same data reach different conclusions about whether a magnetic field is really present. This is typical of cutting-edge science where you're trying to measure something right at the edge of what's possible with current technology. Only time and better observations will resolve whether the magnetic field is real or an artifact of measurement uncertainty. The gravitational measurements that suggested 3I Atlas might be slightly more massive than its size would indicate have also proven difficult to confirm. Calculating the mass of a distant comet requires observing how it affects other objects gravitationally, which is challenging when the comet isn't passing close to any large asteroids or planets. The mass estimates depend on models of how comets reflect sunlight and how much gas they release, both of which involve uncertainties. If the mass anomaly is real, it could mean the comet is denser than typical comets, perhaps containing more rock and less ice than usual. Alternatively, it could indicate that our size estimates are wrong, and the comet is actually larger than we think. Or it could suggest something more exotic, like the comet containing unusual materials with higher density than normal ice and rock. Without sending a spacecraft to the comet for direct measurements, we can't definitively resolve these questions. Space weather forecasters have been monitoring the sun extra carefully as 3I Atlas approaches. They're watching for any signs that solar activity is increasing beyond normal levels for this phase of the solar cycle. So far, the sun has been behaving normally for solar maximum. Lots of sunspots, frequent small flares, and occasional larger eruptions. Nothing has stood out as obviously anomalous. The critical period will be the days immediately before, during, and after perihelion on October 29th. This is when 3I Atlas will be closest to the sun and experiencing maximum heating. If the comet is going to trigger enhanced solar activity, this is when it would most likely happen. Satellites positioned to observe both the sun and the comet will be collecting data continuously during this period. Whatever happens at perihelion, scientists will learn something valuable. If nothing unusual occurs, it will confirm that even exotic interstellar comets don't significantly affect solar behavior. This would be reassuring and would help us predict what will happen when we encounter future interstellar visitors. If something unusual does occur, it would open up entirely new areas of research about how comets interact with stars and whether external triggers can influence solar activity. The countdown continues. Days become hours, hours become minutes. The universe doesn't care about our uncertainty or our anxiety. 3I Atlas follows its orbit according to the inexorable laws of gravity and motion. Our sun continues its cycles of activity, driven by internal processes that have operated for billions of years. These two objects, one familiar and one alien, are about to have their closest encounter, and we get to watch it happen and learn from it. That's the beauty of living in this age of scientific discovery. Conclusion: what it all means. As we reach the end of this journey through the story of 3I Atlas, it's worth reflecting on what this visitor from another star system teaches us about science, the universe, and ourselves. First, 3I Atlas reminds us that the universe is full of surprises. No matter how much we learn, there are always new discoveries waiting. Just when we think we understand how comets work, nature shows us a comet with chemistry that doesn't fit our models. This should make us humble about the limits of our knowledge, while also excited about all the mysteries remaining to be solved. Second, the comet demonstrates the power of the scientific method. When faced with something unusual and unprecedented, scientists don't guess or speculate wildly. They gather data carefully. They test hypotheses against observations. They revise their understanding based on evidence. They admit uncertainty when appropriate. This systematic, disciplined approach to understanding nature is humanity's most powerful tool for learning about reality. Third, 3i Atlas shows us how interconnected our modern world has become. The comet is being studied by astronomers on every continent. Data is shared instantly across borders. Scientists collaborate regardless of nationality or language. The questions we're asking and the knowledge we're gaining belong to all humanity, not to any single nation or group. This global scientific community represents one of humanity's greatest achievements. Fourth, the story teaches us about risk, probability, and how to think about uncertain futures. We can't predict with certainty what 3i Atlas will do at perihelion. We can assess probabilities and prepare for various scenarios while accepting that some uncertainty is unavoidable. Learning to live with uncertainty while taking reasonable precautions is a crucial life skill that applies far beyond astronomy. Fifth, 3i Atlas reminds us why space exploration and scientific research matter. The knowledge we gain from studying this comet has no immediate practical application. It won't cure diseases or improve agriculture or make anyone wealthy, but it expands human understanding of the universe. It inspires young people to pursue careers in science and engineering. It demonstrates humanity's ability to work together toward shared goals. These intangible benefits justify the investment in telescopes, satellites, and the scientists who use them. Most importantly, 3i Atlas reminds us that we live in an amazing time. You are alive during the era when humanity first confirmed that objects from other star systems visit ours. You're witnessing discoveries that answer questions humans have wondered about for thousands of years. You have access to information and images that earlier generations couldn't have imagined. You can follow real science as it happens, watching discoveries unfold in real time. The comet will reach perihelion on October 29th, 2025. By the time you read these words, that date might have already passed. 3i Atlas might have swung around the sun and begun its journey back to interstellar space. Or you might be reading this before perihelion, in which case, the crucial observations are still ahead. Either way, the story of 3i Atlas isn't really about what happens on one specific day. It's about humanity's ongoing journey to understand the universe. It's about our capacity for wonder and curiosity. It's about our ability to work together to answer difficult questions. It's about recognizing that we're part of something vastly larger than ourselves. Yet we have the remarkable ability to study and comprehend that larger universe. The night sky has always been our window into the infinite. Ancient peoples looked up and saw gods and myths. We look up and see physics and chemistry, stellar evolution and planetary formation, galaxies and black holes and interstellar visitors. Our understanding has grown immensely, yet the sense of wonder remains. If anything, knowing more about the universe makes it even more amazing, not less. 3i Atlas came from somewhere among those distant stars. It has traveled for millions or billions of years through the cold darkness between solar systems. By chance, its path crossed ours. For a brief moment in cosmic time, we share the same neighborhood. We get to study it, learn from it, and marvel at the fact that we can do these things. Soon, too soon for scientists who wish they had more time to observe, 3i Atlas will leave. It will pass beyond the orbit of Neptune, beyond the Kuiper Belt, beyond the influence of our sun's gravity. It will return to interstellar space, perhaps eventually encountering another star system where other beings might point their telescopes at it and wonder where it came from. But the knowledge we gained will remain. The data collected will be analyzed for years. The questions raised will inspire new research. The sense of connection to the larger cosmos will stay with everyone who followed this story. And someday, when the next interstellar visitor appears, we'll be better prepared to study it because of what 3i Atlas taught us. That's the nature of scientific progress. Each discovery builds on previous ones. Each generation of scientists stands on the shoulders of those who came before. You're part of this continuing story. Whether you become a scientist yourself or simply an educated citizen who understands and appreciates science, you have a role to play in humanity's grand project of understanding the universe. Look up at the night sky when you can. Find a dark place away from city lights if possible. Let your eyes adjust to the darkness. Notice how many stars appear that you couldn't see at first. Think about the fact that most of those stars probably have planets. Consider that some of those planets might be home to other beings, looking at their own night skies and wondering the same things you're wondering. We live in a universe of wonder and mystery. 3i Atlas is just one small part of that universe, but it's a part that came close enough for us to study. It reminded us that space between the stars isn't empty, that visitors from other solar systems pass through ours, and that nature is more diverse and surprising than we imagine. Whatever happened or will happen at perihelion, 3i Atlas has already given us something valuable. A reminder that we're part of a vast, ancient, dynamic universe, full of things we're still discovering. And that's pretty amazing when you think about it. The countdown has ended, or will end, but the story continues. New observations will be made, new papers will be published, new interstellar visitors will be discovered, and humans will continue looking up, wondering, asking questions, and seeking answers. Because that's what we do. That's what makes us human. And 3i Atlas is part of that eternal human quest to understand our place in the cosmos. Thank you for taking this journey through the story of an interstellar visitor. May you always keep that sense of wonder about the universe. May you always ask questions and seek understanding. And may you remember that you're living through an incredible time in human history when we're taking our first real steps toward understanding our place in a galaxy full of mystery and possibility.